Welcome to this scientific lecture on quantized conductance in atomic scale wires and quantum point contacts. Today we will explore one of the most fascinating phenomena in nanoscale physics, where electrical conductance appears in discrete steps rather than smoothly. Let's begin by reviewing what we normally expect from electrical conductance. In our everyday experience with electrical circuits, Ohm's law tells us that conductance should be smooth and continuous. Conductance G equals 1 over resistance R, which can be written as sigma A over L, where sigma is the conductivity, A is the cross-sectional area, and L is the length of the conductor. According to classical physics, if you smoothly change the cross-sectional area of a wire, the conductance should change smoothly and continuously. There should be no jumps or discrete steps. Imagine a wire that gradually narrows. Classically, we expect the resistance to increase smoothly as the wire becomes thinner and the conductance to decrease smoothly. But is this what actually happens at the atomic scale? Now let me tell you what actually happens when we shrink a conductor down to nanometer or atomic dimensions. Something remarkable occurs that completely contradicts our classical intuition. When experimentalists carefully measure the conductance of ultra-narrow wires or quantum point contacts, they observe that the conductance does not change smoothly. Instead, it changes in discrete, well-defined steps. Here is what the experimental data looks like. As we vary the width of the constriction, the conductance jumps between discrete values. These are the famous conductance plateaus. These discrete steps are not random. They are multiples of a fundamental unit called the conductance quantum. The conductance quantum G sub 0 equals 2e squared over h, where e is the elementary charge and h is Planck's constant. Numerically, this equals approximately 7.75 times 10 to the minus 5 Siemens, or equivalently, the resistance quantum is about 12.9 kilo ohms. Notice the factor of 2 in the numerator. This accounts for the spin degeneracy of electrons. Each spatial quantum state can accommodate 2 electrons, one with spin up and one with spin down. Now you might be asking yourself, why does this quantization occur? What is the physical mechanism behind these discrete conductance steps? Let me explain the beautiful physics underlying this phenomenon. The key to understanding quantized conductance lies in recognizing the wave nature of electrons. At nanometer scales, we cannot treat electrons as classical particles. We must use quantum mechanics. The de Broglie wavelength lambda equals h over p equals h over m versus. For electrons at typical energies in conductors, this wavelength is on the order of nanometers. When the width of the conductor becomes comparable to, or smaller than the electron wavelength, quantum mechanical effects become dominant. The electrons can no longer move freely in all directions. In a narrow channel, electrons form standing waves in the transverse direction. These are called transverse modes or subbands. Each mode corresponds to a different way the electron wave can fit across the width of the channel. Let me explain transverse quantization in more detail. This is the heart of the phenomenon. The transverse momentum is quantized. K sub y equals n pi over w, where n is a positive integer and w is the width of the channel. Each transverse mode has an energy E sub n equals h bar squared k sub y squared over 2 meters, which equals n squared pi squared h bar squared over 2 meters w squared. These are the subband energies. Here's a helpful analogy. Think of organ pipes. Just as organ pipes of different lengths produce different musical notes, electron waves in narrow channels can only oscillate at certain allowed frequencies. The narrower the pipe or channel, the higher the fundamental frequency. Now let's connect this transverse quantization to the conductance. How does the number of occupied modes relate to the measured conductance? The conductance G equals 2e squared over h times n, where n is the number of transverse modes that are occupied and contributing to transport. This is the Landauer formula for ballistic transport. Each occupied transverse mode contributes exactly 1 conductance quantum. This is a profound result that connects the quantum mechanical mode structure to macroscopic conductance. You might wonder, what do we mean by ballistic transport? This is an important concept. Ballistic transport means that electrons travel through the conductor without scattering. They move like bullets through the channel. This requires that the channel length is shorter than the mean free path. In quantum point contacts, the narrow constriction is typically only a few tens of nanometers long. At low temperatures, this is much shorter than the electron mean free path, so the transport is indeed ballistic. Here's a schematic showing electrons moving ballistically through a quantum point contact. They enter from the wide region, pass through the narrow constriction without scattering, and exit into the other wide region. Let me give you a deeper understanding of the Landauer formula and why each mode contributes exactly one conductance quantum. More generally, the conductance equals 2e squared over h times the sum over all modes of the transmission probability T sub n. For perfect transmission, T sub n equals 1. This formula is remarkable because it connects purely quantum mechanical quantities like transmission probabilities to something we can measure with a simple voltmeter and ammeter. It's a beautiful bridge between quantum and classical worlds. Now let's address why this phenomenon seems to contradict our Ohm's law intuition. What's going on here? The usual derivation of Ohm's law assumes diffusive transport. Electrons are assumed to undergo many scattering events as they traverse the conductor. The resistance arises from these scattering processes. But in ballistic quantum transport, through a perfect quantum point contact, there is no scattering inside the narrow constriction. The electrons pass through without any resistance from scattering. This raises a fascinating question. If there's no scattering, where does the resistance come from? Why isn't the conductance infinite? The answer is subtle and beautiful. The resistance comes from the contact between the wide electron reservoirs and the narrow quantum channel. Not all electrons incident from the reservoir can enter the narrow channel modes. This is fundamentally different from the scattering resistance we're used to. It's called contact resistance or interface resistance. It arises from the quantum mechanical mismatch between the wide and narrow regions. The electrons in the wide reservoirs have many available states, but only certain modes can couple into the narrow channel. This mode mismatch is the origin of the quantum resistance. How do experimentalists actually create and measure quantum point contacts? Let me describe the experimental techniques. The most common method uses a split gate technique on a two-dimensional electron gas. This is typically realized in a gallium arsenide aluminum gallium arsenide heterostructure cooled to liquid helium temperatures. Another method uses mechanically controllable break junctions. A thin metallic wire is stretched until it breaks, and at the moment just before breaking, it forms an atomic scale contact showing conductance quantization. A third method uses scanning tunneling microscope tips to create atomic scale contacts between the tip and a metallic surface. Here's a schematic of the split gate technique. Two metal gates are fabricated above a two-dimensional electron gas. When negative voltage is applied to the gates, they deplete the electrons underneath, creating a narrow constriction whose width can be tuned by the gate voltage. One crucial aspect of these experiments is the temperature requirement. Why must these measurements be done at very low temperatures? The thermal energy K sub Bt must be much less than the subband spacing delta E. Otherwise, thermal fluctuations wash out the quantization. For typical quantum point contacts with widths of tens of nanometers, this requires temperatures below about 4 Kelvin, which is why liquid helium cooling is necessary. Let me give you some helpful analogies to solidify your understanding of conductance quantization. Think of a highway with multiple lanes. Each lane can carry a certain flow of traffic. If you suddenly narrow a multi-lane highway to a single lane, the traffic flow is limited by that single lane, regardless of how many lanes feed into it. Similarly, the conductance is determined by the number of quantum modes in the narrowest part. Another analogy is water flowing through pipes. If you have several narrow pipes in parallel, each pipe contributes independently to the total flow. Similarly, each quantum mode contributes independently to the total conductance. Before we conclude, let me mention an interesting advanced topic. Under certain conditions, fractional quantization can occur. When a strong magnetic field is applied perpendicular to the two-dimensional electron gas, the conductance can be quantized at fractional multiples of E squared over h. This is related to the fractional quantum Hall effect. Also, if the quantum point contact is not perfectly transmitting, meaning the transmission probability is less than 1, the conductance can take non-integer multiples of the conductance quantum. What is the broader significance of conductance quantization? Why should we care about this phenomenon beyond its fundamental interest? First, it provides a fundamental resistance standard based on fundamental constants. The quantized Hall resistance is now used to define the ohm in the International System of Units. Second, quantum point contacts serve as an ideal testing ground for theories of quantum transport. They are the simplest possible quantum transport devices. Third, they are building blocks for more complex quantum devices, including quantum dots, single electron transistors, and potentially quantum computing architectures. Conductance quantization is a prime example of mesoscopic physics, which deals with systems intermediate between macroscopic and microscopic. Mesoscopic systems are neither fully quantum mechanical like individual atoms, nor fully classical like bulk materials. They exhibit a fascinating interplay of quantum and classical behavior. In mesoscopic devices like quantum point contacts, quantum coherence is maintained across the entire structure. The electron wave function remains coherent from one side to the other. The theoretical framework that describes conductance quantization is called the Landauer-Bodecker formalism. Let me briefly explain this powerful approach. The current I equals 2e over h times the integral of f sub L of E minus f sub R of E times T of E dE, where f sub L and f sub R are the Fermi functions in the left and right reservoirs, and T of E is the energy-dependent transmission. This formalism treats electrical current as the transmission of electrons between equilibrium reservoirs at different chemical potentials. It's fundamentally different from the traditional Drude approach. Let me summarize the key concepts we've covered in this lecture. First, conductance is quantized in units of 2e squared over h when conductors are shrunk to the nanoscale, showing discrete steps rather than smooth variation. Second, this quantization arises from the quantization of transverse modes. Electrons form standing waves across the width of the channel, and only discrete modes are allowed. Third, in ballistic transport, each occupied transverse mode contributes exactly one conductance quantum to the total conductance. Fourth, the resistance in perfect quantum point contacts comes from contact resistance at the interface between wide and narrow regions, not from scattering inside the conductor. Fifth, this phenomenon contradicts our Ohm's law intuition, because Ohm's law assumes diffusive transport with many scattering events, while quantum point contacts exhibit ballistic transport. Conductance quantization is a beautiful manifestation of quantum mechanics in an easily measurable macroscopic quantity. It reminds us that at small scales, the wave nature of electrons becomes paramount. This phenomenon demonstrates the power and beauty of quantum mechanics operating in the mesoscopic regime, bridging the gap between individual atoms and bulk materials. The discovery and understanding of conductance quantization has opened entirely new directions in both fundamental physics and practical nanotechnology. Thank you for your attention. I hope this lecture has given you a deep appreciation for the quantum mechanical nature of electrical conduction at the nanoscale.